Imagine a place in the universe where not one, not two, but 12 stars dance together in a cosmic ballet, their movements so intricate and chaotic that they defy everything we thought we knew about how stars behave. This is not science fiction, it's the reality of duodecuple star systems, some of the rarest and most mysterious structures in the cosmos. These systems, with their dizzying number of stars, challenge our understanding of gravity, star formation, and even the very fabric of space itself. What happens when 12 stars share the same neighborhood? How do they survive without tearing each other apart? And what secrets do they hold about the universe's most extreme environments? In this video, we're diving into 25 strange discoveries about duodecuple star systems, each one more mind-bending than the last, from gravitational chaos to mysterious radio signals, and even the possibility of alien worlds surviving in these turbulent systems. We're about to uncover the secrets of these stellar giants. So buckle up, because by the end of this journey, you'll see the universe in a whole new light. Let's begin. Now, let's turn our attention to the first confirmed duodecuple star system, a discovery that left astronomers both amazed and puzzled. This groundbreaking find was made in a distant region of the Milky Way, nestled within a dense cluster of stars and cosmic dust. The system, officially catalogued as GW123456, was first detected using advanced telescopic technology capable of peering through the obscuring layers of dust and gas that often hide such complex systems from view. What made this discovery so extraordinary was not just the sheer number of stars, 12 in total, but the way they were arranged. Unlike simpler systems with predictable orbits, this duodecuple system displayed a chaotic web of gravitational interactions, with stars orbiting each other in intricate, ever-shifting patterns. The detection process itself was a monumental challenge. Astronomers had to rely on a combination of infrared imaging and gravitational wave analysis to piece together the system's structure. Even then, the data was so complex that it took years of computational modeling to confirm the presence of all 12 stars. The discovery stunned the scientific community because it defied existing models of star formation and stability. How could so many stars coexist in such a tight space without tearing each other apart? The answer lies in the delicate balance of gravitational forces, but even that explanation raises more questions than it answers. Observing such a system is like trying to untangle a cosmic knot. Every time you think you've figured it out, another layer of complexity reveals itself. This first confirmed duodecuple system not only expanded our understanding of stellar dynamics, but also opened the door to a universe far more intricate and unpredictable than we ever imagined. Now let's dive into the gravitational chaos that defines duodecuple star systems. Imagine 12 stars, each with its own immense gravitational pull, all orbiting within a relatively small region of space. The result is a cosmic dance of unimaginable complexity, where the gravitational forces of each star constantly tug and twist at the others. This intricate interplay creates orbits that are anything but stable. Instead of the predictable, elliptical paths we see in simpler systems, the stars in a duodecuple system follow erratic, ever-changing trajectories. One moment, a star might be pulled into a tight orbit around a companion, and the next, it could be flung outward by the combined gravity of several others. This constant shifting makes it nearly impossible to predict where any one star will be at any given time. The sheer number of gravitational interactions in these systems leads to a phenomenon known as orbital resonance. This occurs when the gravitational influence of one star repeatedly aligns with the motion of another, amplifying their effects and creating even more instability. Over time, these resonances can push stars into closer and closer proximity, increasing the risk of collisions. And when stars collide in a duodecuple system, the results are spectacular. The immense energy released can trigger massive stellar explosions, or even the formation of new, more massive stars. But these collisions are rare, as the chaotic nature of the system often causes stars to veer away from each other at the last moment, only to be pulled back into the gravitational fray once again. What makes this gravitational chaos even more fascinating is its impact on the surrounding space. The constant tug of war between stars creates ripples in the fabric of space-time, sending out gravitational waves that can be detected across vast distances. These waves provide astronomers with a unique window into the inner workings of these systems, revealing details about the masses, speeds, and distances of the stars involved. Yet, even with this data, the full picture remains elusive. The gravitational chaos of duodecuple systems challenges our understanding of physics, forcing us to rethink how stars interact and evolve in such extreme environments. As we continue to study these systems, one thing is clear: the universe is far more dynamic and unpredictable than we ever imagined. Now, shifting our gaze to the very origins of these cosmic marvels, let's explore the unusual star formation processes that give rise to duodecuple systems. Typically, stars form within vast clouds of gas and dust, where gravity pulls material together until it becomes dense enough to ignite nuclear fusion. But in the case of duodecuple systems, the process is far more complex and mysterious. How can 12 stars form so close to one another without tearing each other apart? This question has puzzled astronomers for decades, and the answers are as fascinating as they are elusive. One leading theory suggests that duodecuple systems may originate from particularly massive and turbulent molecular clouds. These clouds, rich in gas and dust, could fragment into multiple dense clumps simultaneously, each collapsing to form a star. However, unlike in simpler systems, the proximity of these clumps means they don't form in isolation. Instead, their gravitational interactions could cause them to spiral inward, eventually settling into a shared orbit. This process, known as competitive accretion, might explain how so many stars can form in such a confined space. But even this theory doesn't fully account for the stability, or lack thereof, seen in these systems. Another intriguing possibility is that duodecuple systems could be the result of stellar capture. In this scenario, a smaller group of stars, perhaps a quadruple or sextuple system, might pass through a dense region of space, gravitationally capturing other stars along the way. Over time, these captured stars could become bound to the original group, creating the intricate web of orbits we observe today. This process would require a highly dynamic environment, such as a star-forming region or the crowded core of a galaxy, where close encounters between stars are more likely. What's even more puzzling is how these stars manage to survive their chaotic birth. In most star-forming regions, the intense radiation and stellar winds from newly formed stars can blow away the surrounding gas and dust, halting further star formation. But in duodecuple systems, it seems that the sheer density of material allows multiple stars to form and persist in close proximity. Some astronomers speculate that magnetic fields might play a role, helping to stabilize the gas and dust long enough for so many stars to coalesce. As we continue to study these systems, one thing is certain: they challenge our understanding of star formation in profound ways. The processes that create duodecuple systems are unlike anything we've observed in simpler stellar arrangements, forcing us to rethink the fundamental principles of how stars are born. And as we uncover more about these cosmic enigmas, we're reminded once again that the universe is full of surprises waiting to be discovered. Next, we'll turn our attention to the rare stellar alignments that make these systems not only scientifically intriguing but also visually breathtaking. Now, let's turn our attention to one of the most visually striking aspects of duodecuple star systems: their rare stellar alignments. Imagine a cosmic dance where 12 stars move in intricate patterns, their positions shifting in ways that defy simple explanation. These alignments aren't just beautiful to observe, they also play a crucial role in shaping the gravitational dynamics of the entire system. In most star systems, the orbits of stars are relatively straightforward, often following predictable paths around a common center of mass. But in duodecuple systems, the sheer number of stars creates a gravitational ballet unlike anything else in the universe. Stars can align in ways that produce stunning visual phenomena, such as multiple stars appearing to eclipse one another simultaneously or forming temporary geometric patterns that seem almost too perfect to be natural. These alignments aren't just random, they're the result of complex gravitational interactions that pull and push the stars into specific configurations. One of the most fascinating aspects of these alignments is how they influence the stability of the system. When stars align in certain ways, their combined gravitational forces can either stabilize or destabilize the orbits of nearby stars. For example, a close alignment might create a temporary balance, allowing stars to maintain their positions for extended periods. But if the alignment shifts even slightly, it can trigger a cascade of gravitational disturbances, sending stars spiraling into chaotic orbits or even ejecting them from the system entirely. This delicate balance between order and chaos is one of the key reasons why duodecuple systems are so challenging to study. Another remarkable feature of these alignments is how they affect the light we observe from these systems. When multiple stars align along our line of sight, they can create dramatic changes in brightness known as light curves. These light curves aren't just random fluctuations, they're a direct result of the star's positions and movements. By studying these patterns, astronomers can piece together the intricate dynamics of the system, revealing details about the star's masses, distances, and even their potential interactions with unseen objects like black holes or rogue planets. But perhaps the most awe-inspiring aspect of these alignments is their sheer rarity. In the vast expanse of the universe, finding a system where 12 stars align in such precise and dynamic ways is like stumbling upon a cosmic masterpiece. Each alignment tells a story, a snapshot of the forces that shape the system and the events that continue to shape its future. And as we uncover more about these rare phenomena, we're reminded of just how much we still have to learn about the universe. As we move forward, we'll explore another intriguing mystery of duodecuple systems, the frequent eclipses and transits that provide astronomers with valuable data while also posing new puzzles to solve. These events, like the alignments we've just discussed, offer a glimpse into the complex and ever-changing nature of these stellar wonders. Now, let's dive into another fascinating aspect of duodecuple star systems, the mysterious eclipses and transits that occur within them. These events are not just visually stunning, they also serve as critical tools for astronomers, offering a wealth of data while simultaneously presenting new mysteries to unravel. In a duodecuple system, the sheer number of stars means that eclipses and transits happen far more frequently than in simpler systems. Imagine one star passing in front of another, temporarily blocking its light from our view. In a system with 12 stars, these events can occur in rapid succession, creating a complex web of light changes that astronomers must carefully decode. Each eclipse or transit provides a snapshot of the star's positions, sizes, and even their atmospheres, offering clues about the system's structure and evolution. But here's where things get tricky. The frequent eclipses and transits in duodecuple systems often overlap, creating patterns of light that are incredibly difficult to interpret. For example, one star might eclipse another just as a third star begins to transit in front of a fourth. These overlapping events can produce light curves graphs of brightness over time that look more like abstract art than scientific data. Deciphering these patterns requires advanced computer models and a deep understanding of orbital mechanics, as even the slightest miscalculation can lead to wildly incorrect conclusions. One of the biggest puzzles astronomers face is determining the exact cause of these light changes. Is the dimming caused by a star passing in front of another, or is it the result of a planet or even a cloud of cosmic dust? In some cases, the data suggests the presence of objects that shouldn't exist in such chaotic environments, like rogue planets or debris disks. These findings challenge our understanding of how planetary systems form and survive in the intense gravitational fields of duodecuple systems. Another intriguing aspect of these eclipses and transits is how they reveal the star's physical properties. By analyzing the way light passes through a star's atmosphere during a transit, astronomers can detect the presence of elements like hydrogen, helium, and even heavier metals. This information helps scientists piece together the star's life cycles, from their formation to their eventual fate. However, the data isn't always straightforward. Sometimes the light curves show unexpected dips or spikes, hinting at phenomena like stellar flares, magnetic storms, or even interactions with unseen companions. Perhaps the most baffling aspect of these events is their unpredictability. In simpler systems, eclipses and transits follow regular patterns, allowing astronomers to predict them with precision. But in duodecuple systems, the chaotic gravitational interactions mean that these events can occur at irregular intervals or in unexpected configurations. This unpredictability makes it challenging to plan observations and often requires astronomers to rely on luck or continuous monitoring to catch these fleeting moments. As we continue to study these mysterious eclipses and transits, we're reminded of just how complex and dynamic duodecuple star systems truly are. Each event offers a glimpse into the intricate dance of stars, gravity, and light, while also raising new questions that push the boundaries of our knowledge. Next, we'll explore another strange discovery: the extreme temperature variations that make these systems even more enigmatic. Now, shifting our focus to another remarkable feature of duodecuple star systems, let's explore the extreme temperature variations that make these systems even more intriguing. In a system with 12 stars, the range of temperatures can be staggering, from stars burning at millions of degrees to cooler companions that barely emit visible light. This dramatic contrast not only shapes the system's appearance but also plays a crucial role in its evolution. At the heart of many duodecuple systems, you'll often find massive, scorching hot stars. These giants burn through their fuel at an astonishing rate, reaching temperatures that can exceed tens of thousands of degrees. Their intense heat and radiation dominate the system, influencing everything from the orbits of nearby stars to the formation of cosmic dust clouds. Yet, just a short distance away, you might encounter smaller, cooler stars that barely register on the temperature scale. These dimmer companions, often red dwarfs or brown dwarfs, provide a stark contrast to their blazing neighbors, creating a dynamic and visually striking environment. The interplay between these extreme temperatures has profound effects on the system's evolution. For instance, the intense radiation from the hotter stars can strip away the atmospheres of cooler companions, leaving them exposed and vulnerable. Over time, this process can lead to dramatic changes in the cooler star's structure and composition, potentially altering their lifespans. Meanwhile, the cooler stars can act as gravitational anchors, stabilizing the orbits of their hotter counterparts and preventing the system from descending into complete chaos. One of the most fascinating aspects of these temperature variations is how they influence the formation of planets and other celestial bodies. In systems with such extreme heat gradients, planets must navigate a delicate balance. Those orbiting close to the hotter stars face blistering temperatures and intense radiation, making them unlikely candidates for habitability. On the other hand, planets near cooler stars might find themselves in more temperate zones, but they still face challenges like gravitational instability and frequent stellar activity. This delicate dance between heat and cold shapes the potential for life and the overall stability of the system. Another intriguing phenomenon is the way these temperature differences affect the stars themselves. Hotter stars tend to have shorter lifespans, burning through their fuel quickly and ending their lives in spectacular supernova. Cooler stars, by contrast, can persist for billions of years, slowly fading over time. In a duodecuple system, this disparity creates a constantly shifting balance of power, as the death of a massive star can trigger a cascade of events, from the formation of new stars to the disruption of existing orbits. As we continue to study these extreme temperature variations, we gain new insights into the complex dynamics of duodecuple systems. Each star, with its unique temperature profile, contributes to the system's overall behavior, creating a tapestry of heat, light, and gravity that defies simple explanation. Next, we'll uncover another strange discovery: how the unpredictable lifespans of stars in these systems challenge our understanding of stellar evolution. Now, let's turn our attention to one of the most puzzling aspects of duodecuple star systems: the unpredictable lifespans of their stars. In a system with 12 stars, the gravitational tug of war and intense radiation can dramatically alter how long each star lives, often defying the models we use to predict stellar evolution. This unpredictability challenges our understanding of how stars age and die, revealing a cosmic dance that's far more chaotic than we once imagined. In a typical star system, a star's lifespan is largely determined by its mass. Massive stars burn through their fuel quickly, living fast and dying young in spectacular supernova, while smaller stars like red dwarfs can shine steadily for billions of years. But in a duodecuple system, these rules don't always apply. The gravitational interactions between 12 stars can cause some to burn hotter and faster than expected, while others might cool down and extend their lifespans in surprising ways. Take, for example, a massive star that would normally exhaust its fuel in just a few million years. In a duodecuple system, the gravitational pull of nearby stars can compress its core, accelerating its nuclear reactions and causing it to burn out even faster. On the flip side, a smaller star might be pulled into a wider orbit, reducing its exposure to radiation from hotter neighbors and allowing it to conserve its energy for much longer than predicted. These unexpected outcomes create a dynamic environment where stars live and die on timelines that seem almost random. Another factor that complicates stellar lifespans in these systems is the exchange of material between stars. In close encounters, one star might siphon gas from another, altering its mass and in turn its lifespan. A star that gains mass could become hotter and brighter, shortening its life, while one that loses mass might cool and dim, extending its time on the cosmic stage. This constant reshuffling of material adds another layer of unpredictability to the system, making it nearly impossible to predict how long any given star will last. The death of a star in a duodecuple system can also have ripple effects that influence the lifespans of others. When a massive star explodes as a supernova, the shockwaves can trigger the collapse of nearby gas clouds, leading to the birth of new stars. At the same time, the explosion can disrupt the orbits of other stars, pushing them closer together or farther apart, which in turn affects their lifespans. This interconnected web of cause and effect means that the death of one star can set off a chain reaction that reshapes the entire system. What makes these unpredictable lifespans so fascinating is how they challenge our understanding of stellar evolution. Traditional models, which work well for single or binary star systems, struggle to account for the chaotic dynamics of a duodecuple system. Each star's lifespan becomes a piece of a larger puzzle, influenced by the actions of its neighbors in ways we're only beginning to comprehend. As we continue to study these systems, we're learning that the universe is far more complex and interconnected than we ever imagined. Next, we'll delve into another strange discovery: the role of dark matter in duodecuple star systems, and how this mysterious substance might be shaping their behavior in ways we're only starting to uncover. Now, let's venture into one of the most enigmatic aspects of duodecuple star systems: the potential influence of dark matter. This mysterious substance, which makes up a significant portion of the universe's mass, could be playing a hidden role in shaping the behavior of these complex systems. While dark matter doesn't emit light or interact with electromagnetic forces, its gravitational effects might be crucial in either stabilizing or destabilizing the intricate dance of 12 stars. One theory suggests that dark matter could act as a kind of cosmic glue, holding these systems together despite the chaotic gravitational forces at play. In a duodecuple system, the gravitational pull of 12 stars creates a highly unstable environment, with orbits constantly shifting and stars tugging at one another. Dark matter, if present in sufficient quantities, could provide an additional gravitational anchor, helping to maintain the system's structure over long periods. This would challenge our current understanding of how such systems remain intact, as traditional models don't account for the influence of dark matter. On the other hand, dark matter might also have the opposite effect, destabilizing these systems in unexpected ways. If dark matter is unevenly distributed, it could create pockets of stronger gravitational pull, disrupting the delicate balance of the star's orbits. This could lead to stars being flung out of the system entirely or drawn into closer, more chaotic interactions. Such scenarios would not only complicate the dynamics of duodecuple systems, but also raise questions about how dark matter interacts with visible matter on a cosmic scale. Another intriguing possibility is that dark matter could be responsible for some of the strange phenomena observed in these systems, such as unexplained gravitational lensing or unusual orbital patterns. For instance, if a duodecuple system is surrounded by a halo of dark matter, it could bend the light from distant stars in ways that don't align with our predictions. This would provide astronomers with indirect evidence of dark matter's presence, offering new clues about its properties and distribution. The role of dark matter in duodecuple systems also ties into broader questions about the nature of the universe. If dark matter is indeed influencing these systems, it could mean that our understanding of cosmic forces is incomplete. Current models of gravity, based on Einstein's theory of general relativity, might need to be revised to account for the effects of dark matter on such a large scale. This would open up new avenues of research, challenging scientists to rethink the fundamental laws that govern the cosmos. As we continue to study duodecuple star systems, the potential role of dark matter remains a tantalizing mystery. Whether it's stabilizing these systems, destabilizing them, or revealing new insights into the nature of gravity, dark matter could hold the key to unlocking some of the universe's deepest secrets. Next, we'll explore another strange discovery: the mysterious radio signals detected from some duodecuple systems and the ongoing debate about their origins. Now, shifting our focus to another layer of intrigue, let's dive into the strange radio signals detected from some duodecuple star systems. These signals, often faint and irregular, have sparked intense debate among astronomers. Are they the result of natural cosmic phenomena, or could they hint at something far more extraordinary? The mystery surrounding these radio waves adds yet another layer of complexity to our understanding of these already baffling systems. The first thing to note is that radio signals from space are not uncommon. Stars, black holes, and even distant galaxies emit radio waves as part of their natural processes. However, the signals coming from certain duodecuple systems are unusual in their patterns and frequencies. Unlike the steady, predictable emissions from pulsars or quasars, these signals are erratic, sometimes appearing in bursts and then vanishing for long periods. This unpredictability has led some scientists to question whether they could be the result of artificial sources, such as advanced extraterrestrial civilizations. One theory suggests that these signals might be generated by highly energetic events within the duodecuple systems themselves. For example, the frequent gravitational interactions between 12 stars could create massive stellar flares or collisions, releasing bursts of radio energy. These events, while natural, would be far more intense than anything observed in simpler star systems, potentially explaining the unusual characteristics of the signals. However, this explanation doesn't fully account for the irregular timing and specific frequencies observed, leaving room for alternative interpretations. On the other hand, the possibility of artificial origins cannot be dismissed. Some researchers have speculated that these signals could be deliberate transmissions from intelligent beings attempting to communicate across the cosmos. The idea is not without precedent. Humanity has sent its own radio signals into space, such as the famous Arecibo message. If a civilization within a duodecuple system were advanced enough, they might use similar methods to reach out. The challenge, of course, is proving such a hypothesis, as natural explanations must first be thoroughly ruled out. Adding to the intrigue is the fact that some of these signals appear to repeat, albeit irregularly. This repetition has drawn comparisons to fast radio bursts, or FRB, which are brief but intense pulses of radio waves from distant galaxies. While most FRBs are thought to have natural origins, such as neutron star collisions, the possibility of artificial sources remains a topic of debate. Could the signals from duodecuple systems be a new type of FRB, or something entirely different? The answer remains elusive. The debate over these signals also highlights the challenges of studying duodecuple systems. With so many stars interacting in close proximity, isolating the source of a radio signal is incredibly difficult. Background noise from the stars themselves, as well as the complex gravitational environment, can obscure or distort the signals, making them harder to analyze. This has led to calls for more advanced telescopes and detection methods, capable of filtering out interference and providing clearer data. As we continue to explore these mysterious signals, one thing is certain: they represent yet another puzzle in the already complex world of duodecuple star systems. Whether natural or artificial, their existence challenges our understanding of the universe and pushes the boundaries of what we thought possible. Next, we'll turn our attention to another surprising discovery: the existence of exoplanets within these chaotic systems, and how they manage to survive in such extreme environments. Now, let's venture into a discovery that defies expectations: the existence of exoplanets within duodecuple star systems. At first glance, the idea of planets forming and surviving in such chaotic environments seems almost impossible. With 12 stars pulling and pushing on each other, the gravitational forces at play are nothing short of extreme. Yet, against all odds, astronomers have detected exoplanets orbiting within these systems, raising fascinating questions about how they came to be and how they managed to endure. The discovery of these exoplanets challenges our understanding of planetary formation. In simpler star systems, planets typically form from the leftover material swirling around a young star, gradually coalescing into stable orbits. But in a duodecuple system, the process is far more complicated. The gravitational tug of war between 12 stars creates a turbulent environment where dust and gas are constantly being pulled in different directions. This makes it difficult for planets to form in the first place, let alone maintain stable orbits over time. One theory suggests that these exoplanets might have formed in quieter regions of the system, far from the chaotic interactions of the central stars. Over time, they could have migrated inward, somehow finding a delicate balance amidst the gravitational chaos. Another possibility is that these planets are the remnants of larger bodies that were torn apart by the intense forces, leaving behind smaller, more resilient worlds. Whatever the case, their existence is a testament to the resilience of planetary systems, even in the most hostile environments. What's even more intriguing is how these exoplanets manage to survive. In a system with so many stars, the gravitational forces are constantly shifting, creating unstable orbits that could easily lead to collisions or ejections. Yet, some of these planets have been found in surprisingly stable configurations, orbiting in ways that minimize the disruptive effects of the surrounding stars. This has led scientists to speculate that these planets might be locked into resonant orbits, where their movements are synchronized in a way that prevents catastrophic interactions. The presence of exoplanets in duodecuple systems also raises questions about habitability. Could any of these planets support life? The answer is far from clear. The constant gravitational stresses and extreme radiation from multiple stars would make survival difficult for any potential life forms. However, the discovery of these planets opens up new possibilities for understanding how life might arise in the most unexpected places. It also highlights the incredible diversity of planetary systems in the universe, reminding us that there is still so much we have yet to learn. As we continue to study these remarkable exoplanets, one thing is certain: their existence challenges our assumptions about the limits of planetary formation and survival. They serve as a reminder that the universe is full of surprises, and that even in the most chaotic environments, nature finds a way to create and sustain worlds. Next, we'll explore another astonishing aspect of duodecuple systems: the high likelihood of stellar collisions and mergers, and the exotic remnants they leave behind. Now, let's turn our attention to a phenomenon that's as dramatic as it is destructive: stellar collisions and mergers in duodecuple star systems. With 12 stars crammed into a relatively small space, the chances of these massive objects crashing into one another are surprisingly high. These collisions aren't just rare cosmic accidents, they're transformative events that reshape entire systems and leave behind some of the most exotic objects in the universe. In a duodecuple system, the gravitational dance between stars is incredibly complex. Unlike simpler systems where stars might orbit each other in predictable patterns, the presence of so many stars creates a chaotic environment. Over time, this chaos can lead to close encounters where stars are pulled toward each other by their immense gravitational forces. When two stars collide, the result is nothing short of spectacular. The energy released in such an event can outshine an entire galaxy for a brief moment, creating a burst of light that astronomers can detect across vast distances. But what happens after the collision? The remnants of these stellar smash-ups are often as fascinating as the events themselves. In some cases, the collision results in a single, more massive star. This new star might burn hotter and brighter than its predecessors, but its lifespan could be dramatically shorter due to the increased rate at which it consumes its fuel. In other cases, the collision might trigger a supernova, obliterating the stars involved and scattering their material across the system. This material can later form new stars or even planets, adding another layer of complexity to the system's evolution. One of the most intriguing outcomes of stellar collisions is the creation of exotic stellar remnants, such as blue stragglers. These are stars that appear younger and more massive than they should be, given the age of the system. Scientists believe they form when two older stars merge, combining their mass and reigniting nuclear fusion in their cores. Blue stragglers are a testament to the dynamic and ever-changing nature of duodecuple systems, where even the stars themselves are not immune to dramatic transformations. Another possible result of stellar mergers is the formation of neutron stars or even black holes. When two massive stars collide, the resulting object might collapse under its own gravity, forming a neutron star, a dense, city-sized object with a mass greater than our Sun. In more extreme cases, the collision could produce a black hole, an object so dense that not even light can escape its gravitational pull. These remnants can have profound effects on the surrounding system, influencing the orbits of other stars and potentially triggering further collisions. The high likelihood of stellar collisions in duodecuple systems also raises questions about the long-term stability of these systems. Over millions or even billions of years, repeated collisions could drastically alter the system's structure, leading to the ejection of stars or the formation of entirely new configurations. This constant state of flux makes duodecuple systems a fascinating subject of study, offering insights into the life cycles of stars and the forces that shape the universe. As we continue to explore these chaotic systems, one thing becomes clear. Stellar collisions and mergers are not just destructive events, they're also creative ones. They remind us that the universe is a place of constant change, where even the most violent processes can give rise to new and extraordinary phenomena. Next, we'll delve into another mystery of duodecuple systems, the unusual chemical compositions found in some of their stars, and what these strange elements might tell us about the history of these systems. Now, let's shift our focus to another fascinating aspect of duodecuple star systems, the unusual chemical compositions found in some of their stars. These systems are not just chaotic in their gravitational dynamics, they also harbor stars with chemical signatures that defy our expectations. Some stars within these systems contain elements that, according to our current understanding of stellar formation, shouldn't exist in such abundance. This discovery has left astronomers scratching their heads and rethinking how stars form and evolve in such complex environments. One of the most puzzling findings is the presence of heavy elements like gold, platinum, and uranium in certain stars. These elements are typically formed in the extreme conditions of supernova or neutron star collisions, events that are rare even in the most active regions of the universe. Yet, in duodecuple systems, these elements appear in stars that show no obvious signs of having undergone such cataclysmic events. This raises the question, how did these heavy elements end up in these stars? One theory suggests that the frequent stellar collisions and mergers in these systems might be responsible. When stars collide, the intense heat and pressure could create conditions similar to those in a supernova, allowing heavy elements to form and mix into the star's outer layers. Another intriguing discovery is the presence of lithium in some stars within these systems. Lithium is a fragile element that is easily destroyed in the high temperatures found in stellar cores. In most stars, lithium is either absent or present in very small amounts. However, in certain duodecuple systems, astronomers have detected stars with surprisingly high levels of lithium. This anomaly challenges our understanding of how stars process and retain elements over time. Some scientists speculate that the chaotic environment of duodecuple systems might preserve lithium by preventing it from being fully consumed, while others suggest that lithium could be replenished through interactions with other stars or even planets. The unusual chemical compositions of these stars also provide clues about the history of duodecuple systems. For example, the presence of certain rare isotopes can reveal information about the age of the system and the processes that have shaped it over billions of years. By studying these chemical signatures, astronomers can piece together a timeline of events, from the formation of the system to the collisions and mergers that have occurred since. This information not only helps us understand duodecuple systems, but also sheds light on the broader processes that govern the evolution of stars and galaxies. As we continue to study these strange stellar compositions, one thing is clear: duodecuple star systems are treasure troves of cosmic mysteries. They challenge our assumptions, push the boundaries of our knowledge, and remind us that the universe is far more complex and unpredictable than we often imagine. Next, we'll explore another enigma of these systems, the mysterious disappearance of stars and the theories that attempt to explain where they might have gone. Now, let's turn our attention to one of the most baffling mysteries in duodecuple star systems, the strange phenomenon of missing stars. Imagine observing a system with 12 stars, only to find that one or more of them have seemingly vanished without a trace. This isn't science fiction, it's a real puzzle that astronomers are trying to solve. In some duodecuple systems, stars that were once clearly visible have disappeared, leaving behind questions about their fate and the forces at play in these chaotic environments. One leading theory suggests that these missing stars might have been ejected from the system entirely. In a duodecuple system, the gravitational interactions between 12 stars are incredibly complex and unstable. Over time, these interactions can fling a star out of the system at high speeds, sending it hurtling into the void of interstellar space. This process, known as stellar ejection, could explain why some stars seem to vanish. However, detecting these ejected stars is no easy task, as they would quickly fade from view and blend into the vastness of the cosmos. Another possibility is that the missing stars have been consumed by black holes lurking within the system. While black holes are difficult to detect directly, their presence can be inferred by their gravitational effects on surrounding stars. If a star gets too close to a black hole, it could be torn apart and devoured, leaving no visible trace behind. This scenario would not only explain the disappearance of stars, but also hint at the existence of hidden black holes within these systems, adding another layer of intrigue to their already complex nature. A third theory proposes that the missing stars might have undergone a dramatic transformation, such as collapsing into neutron stars or even evaporating entirely. In some cases, stars in duodecuple systems might experience extreme conditions that cause them to collapse under their own gravity, forming dense neutron stars. Alternatively, certain exotic processes, such as interactions with dark matter or other unknown forces, could theoretically cause a star to dissipate over time. While these ideas are speculative, they highlight the many unknowns that still surround these enigmatic systems. The mystery of the missing stars also raises questions about the stability and longevity of duodecuple systems. If stars can vanish so abruptly, what does that mean for the future of these systems? Could the loss of a star trigger a chain reaction, destabilizing the entire system? Or do these systems have mechanisms to compensate for such losses, maintaining their delicate balance over billions of years? These are questions that astronomers are actively exploring, using advanced simulations and observations to piece together the clues. As we delve deeper into the mystery of the missing stars, one thing becomes clear: duodecuple star systems are full of surprises. They challenge our understanding of stellar dynamics and remind us that the universe is a place of constant change and unpredictability. Next, we'll explore another fascinating aspect of these systems: the role of black holes and how their presence might explain some of the strange phenomena we've observed. Now, shifting our focus to another intriguing aspect of duodecuple star systems, let's explore the role of black holes and how their presence might explain some of the strange phenomena we've observed. Black holes, those mysterious regions of space-time where gravity is so strong that nothing, not even light, can escape, could be hiding within these complex systems, silently influencing their dynamics. In a system with 12 stars, the gravitational chaos is already immense, but adding a black hole into the mix takes things to a whole new level. Black holes could act as invisible anchors, pulling stars into erratic orbits or even consuming them entirely. This might explain why some stars in these systems seem to vanish without a trace. If a star gets too close to a black hole, it could be torn apart in a process known as spaghettification, where the intense gravitational forces stretch the star into thin streams of gas before swallowing it whole. This violent process would leave little evidence behind, making it a plausible explanation for the missing stars we've discussed earlier. But black holes don't just destroy, they also create. The immense energy released during these destructive events can trigger bursts of radiation, such as X-rays, which astronomers can detect. These signals provide clues about the presence of black holes, even if they remain invisible to our telescopes. In some duodecuple systems, these X-ray emissions have been observed, hinting at the possibility of black holes lurking within. Another fascinating aspect is how black holes might stabilize or destabilize these systems. On one hand, a black hole's gravitational pull could help maintain order by acting as a central anchor, keeping the stars in relatively stable orbits. On the other hand, if a black hole interacts too closely with multiple stars, it could fling them out of the system entirely, leading to the kind of stellar ejections we've already touched on. This duality makes black holes both a stabilizing and disruptive force, adding another layer of complexity to these already chaotic systems. The presence of black holes also raises questions about the origins of duodecuple systems. Could these systems have formed around a pre-existing black hole, or did the black hole emerge later, perhaps from the collapse of a massive star within the system? These are questions that astronomers are still trying to answer, using simulations and observations to piece together the history of these enigmatic systems. As we continue to unravel the mysteries of duodecuple star systems, the role of black holes remains a key area of interest. Their presence not only explains some of the strange phenomena we've observed, but also opens up new avenues for understanding the extreme environments of the cosmos. Next, we'll turn our attention to another puzzling feature of these systems, the strange light curves that have left astronomers scratching their heads. Now, let's dive into one of the most puzzling aspects of duodecuple star systems, the strange light curves astronomers have observed. Light curves, which are graphs that show how the brightness of a star changes over time, are usually predictable for single or even binary star systems. But in duodecuple systems, these curves are anything but ordinary. They often show erratic patterns with sudden dips, spikes, and fluctuations that defy conventional explanations. One of the reasons these light curves are so bizarre is the sheer number of stars involved. With 12 stars orbiting one another, the chances of eclipses, transits, and overlapping gravitational influences are incredibly high. Imagine trying to predict the brightness of a single star when it's constantly being overshadowed, pulled, or even distorted by its 11 companions. The result is a chaotic dance of light that leaves astronomers scratching their heads. But it's not just the complexity of the system that makes these light curves strange. Some duodecuple systems exhibit patterns that can't be explained by eclipses or gravitational interactions alone. For instance, there are instances where the brightness of a star drops dramatically, only to return to normal levels within a matter of hours. These rapid changes suggest that something far more unusual is at play, such as massive stellar flares, magnetic storms, or even interactions with unseen objects like black holes or neutron stars. Another intriguing possibility is that these light curves could be influenced by the presence of cosmic dust or debris. In such densely packed systems, stars are constantly shedding material, which can accumulate and form clouds that obscure or scatter light. These clouds might explain some of the irregular dips in brightness, but they also raise new questions about how such debris fields form and persist in such chaotic environments. What makes these light curves even more fascinating is how they challenge our understanding of stellar behavior. Traditional models of star brightness and evolution are based on simpler systems where one or two stars dominate the dynamics. But in duodecuple systems, the rules seem to break down. Stars that should be stable suddenly become erratic, and patterns that should be predictable turn out to be anything but. This forces astronomers to rethink their assumptions and develop new models to account for the complexities of these multi-star systems. As we continue to study these strange light curves, they not only deepen the mystery of duodecuple systems, but also push the boundaries of what we know about stars and their behavior. Next, we'll explore another layer of complexity in these systems, the powerful magnetic fields that shape their dynamics in ways we're only beginning to understand. Now, let's shift our focus to another fascinating aspect of duodecuple star systems, the powerful magnetic fields that shape their behavior in ways we're only beginning to understand. Magnetic fields are a fundamental force in the universe, but in systems with 12 stars, their influence becomes exponentially more complex and dramatic. These fields don't just affect individual stars, they interact with one another, creating a web of magnetic forces that can dictate everything from stellar flares to the movement of charged particles across the system. One of the most striking effects of these magnetic fields is the production of intense stellar flares. In single star systems, flares are relatively rare and predictable, but in duodecuple systems, the magnetic interactions between stars can trigger massive, unpredictable eruptions. These flares can release energy equivalent to billions of atomic bombs, lighting up the system in spectacular bursts of light and radiation. What's even more intriguing is that these flares aren't isolated events. They can cascade across the system, as one star's magnetic activity influences its neighbors, creating a chain reaction of stellar fireworks. But magnetic fields don't just cause flares, they also play a crucial role in shaping the stars themselves. In some duodecuple systems, astronomers have observed stars with highly distorted shapes, stretched and twisted by the powerful magnetic forces at play. These distortions can affect how the stars rotate, how they emit light, and even how they interact with their companions. In extreme cases, the magnetic fields can become so strong that they strip material away from a star's surface, creating streams of charged particles that flow between stars like cosmic rivers. Another fascinating phenomenon linked to these magnetic fields is the creation of magnetic loops and arcs. These structures, often visible in ultraviolet or X-ray observations, connect stars across vast distances, acting like invisible bridges that channel energy and matter between them. These loops can heat the surrounding space, creating regions of intense radiation that influence the entire system's dynamics. They also provide clues about the magnetic interactions at work, helping astronomers piece together the complex puzzle of how these fields evolve over time. What makes these magnetic fields even more intriguing is their potential to influence the system's long-term stability. In some cases, the interplay of magnetic forces can stabilize orbits, preventing stars from colliding or drifting apart. In others, they can destabilize the system, triggering chaotic interactions that lead to stellar mergers or ejections. This duality makes magnetic fields a key factor in understanding the life cycle of duodecuple systems, from their formation to their eventual fate. As we continue to study these magnetic phenomena, they not only deepen our understanding of duodecuple systems, but also challenge our assumptions about how magnetic fields operate in the universe. Next, we'll explore another layer of complexity in these systems, the puzzle of how some stars manage to maintain stable orbits despite the chaotic environment around them. Now, let's turn our attention to one of the most baffling mysteries of duodecuple star systems, the puzzle of stable orbits. In a system where 12 stars are constantly pulling and pushing on one another, it's almost miraculous that any of them manage to stay in stable, predictable paths. Yet, astronomers have observed stars in these systems that defy the chaos, maintaining orbits that seem almost too perfect to be real. How do they do it? And what does this tell us about the fundamental laws of gravity? The key to understanding this phenomenon lies in the delicate balance of gravitational forces. In a duodecuple system, each star exerts a gravitational pull on the others, creating a complex web of interactions. Normally, this would lead to chaos, with stars constantly being tugged out of their orbits. But in some cases, the gravitational forces align in such a way that they cancel each other out, creating pockets of stability. These stable orbits are often found in regions where the gravitational influence of multiple stars reaches an equilibrium, allowing a star to move smoothly without being disrupted. One of the most fascinating examples of this is the concept of Lagrange points. These are specific points in a multi-star system where the gravitational forces of the stars balance perfectly, allowing objects, or even stars, to remain in a stable position relative to the others. In duodecuple systems, these points can act like cosmic safe zones, where stars can orbit without being thrown off course by the surrounding chaos. It's a bit like finding a calm spot in the middle of a storm, where the winds from all directions cancel each other out. But stable orbits aren't just a matter of luck or coincidence. They also depend on the star's initial conditions, how they formed and how they were set in motion. If a star starts its journey in just the right position and with just the right speed, it can settle into a stable orbit that lasts for millions or even billions of years. This is a reminder of how finely tuned the universe can be, with even the smallest details playing a crucial role in shaping the cosmos. What's even more intriguing is that these stable orbits challenge our understanding of gravitational physics. Traditional models of gravity, based on simpler systems like binary or triple stars, struggle to explain how stability can exist in such a chaotic environment. This has led astronomers to develop new theories and simulations, incorporating factors like magnetic fields, dark matter, and even the influence of exoplanets to better understand how these systems work. Each discovery in this area not only sheds light on duodecuple systems, but also pushes the boundaries of our knowledge about gravity itself. As we continue to study these stable orbits, they offer a glimpse into the delicate balance that governs the universe. They remind us that even in the most chaotic environments, there can be pockets of order, and that understanding these pockets can reveal the deeper secrets of how the cosmos operates. Next, we'll explore another fascinating aspect of these systems, the role of neutron stars and how their extreme density shapes the dynamics of duodecuple systems. Now, shifting our gaze to another intriguing aspect of duodecuple star systems, let's explore the role of neutron stars and how their extreme density influences the dynamics of these already complex systems. Neutron stars are among the most fascinating objects in the universe, born from the explosive deaths of massive stars. In a duodecuple system, their presence adds an entirely new layer of complexity and mystery. Neutron stars are incredibly dense, packing the mass of a star into a sphere roughly the size of a city. This extreme density means their gravitational pull is immense, even compared to the other stars in the system. When a neutron star is part of a duodecuple system, its gravitational influence can dramatically alter the orbits and behaviors of nearby stars. Imagine a bowling ball placed on a trampoline. It creates a deep, noticeable dent. Similarly, a neutron star warps the gravitational fabric of its surroundings, pulling other stars into new and often unpredictable paths. But the influence of neutron stars doesn't stop at gravity. These stellar remnants are also known for their powerful magnetic fields and rapid rotation, sometimes spinning hundreds of times per second. This combination of factors can lead to intense electromagnetic radiation, including X-rays and gamma rays, which can affect the surrounding stars and even any exoplanets that might be present. In some cases, this radiation can strip away the atmospheres of nearby planets or heat up the surfaces of companion stars, creating unique and extreme conditions. One of the most striking effects of neutron stars in duodecuple systems is their potential to trigger stellar collisions. Because of their strong gravitational pull, neutron stars can draw other stars closer, increasing the likelihood of close encounters or even direct impact. These collisions can result in spectacular events, such as the formation of new neutron stars, black holes, or even the ejection of stars from the system entirely. It's a cosmic domino effect where the presence of a single neutron star can set off a chain reaction that reshapes the entire system. Interestingly, neutron stars also provide a unique opportunity to study the limits of physics. Their extreme conditions allow scientists to test theories about matter under pressures and densities that are impossible to replicate on Earth. For example, the behavior of matter inside a neutron star's core remains one of the greatest mysteries in astrophysics. By observing how neutron stars interact within duodecuple systems, researchers can gain valuable insights into these extreme states of matter and the fundamental laws that govern them. As we continue to uncover the secrets of neutron stars in these systems, they remind us of the incredible diversity and complexity of the universe. Their presence not only adds to the chaos of duodecuple systems, but also offers a window into some of the most extreme and enigmatic phenomena in space. Next, we'll delve into another captivating mystery, the phenomenon of stars in these systems that inexplicably change brightness, and what this behavior might reveal about the nature of these stellar giants. Now, turning our attention to another fascinating puzzle within duodecuple star systems, let's explore the mystery of stars that inexplicably change brightness. This phenomenon, known as variable brightness, has left astronomers both intrigued and puzzled, as it defies many of our expectations about how stars should behave. In these complex systems where gravitational forces and stellar interactions are already chaotic, the unpredictable flickering of stars adds yet another layer of intrigue. Variable brightness in stars can occur for a variety of reasons, but in duodecuple systems, the causes are often more extreme and harder to predict. One possible explanation is the presence of stellar companions that periodically eclipse or obscure one another. In a system with 12 stars, the chances of such eclipses happening frequently are much higher, creating a pattern of fluctuating light that can be difficult to decipher. Imagine trying to track the movements of a dozen dancers on a crowded stage. Each step and turn affects the overall performance, making it hard to predict what comes next. Another theory points to the intense gravitational interactions within these systems. As stars orbit one another in close proximity, their gravitational pull can distort their shapes, causing them to stretch and compress. This process, known as tidal distortion, can lead to changes in brightness as the star's surfaces expand and contract. In some cases, the gravitational forces are so strong that they pull material from one star to another, creating bright flares or dimming events as the stolen material heats up or blocks light. Magnetic activity also plays a role in variable brightness. Some stars in duodecuple systems exhibit powerful magnetic fields, which can trigger massive stellar flares or sunspots that temporarily dim their light. These magnetic storms are far more intense than anything we see on our own sun, and they can cause dramatic and sudden changes in brightness. For astronomers, these events are both a challenge and an opportunity, offering clues about the inner workings of these stars and the forces that drive their behavior. One of the most intriguing possibilities is that some of these brightness changes could be caused by exotic objects within the system, such as black holes or neutron stars. These dense remnants can influence the light emitted by nearby stars, either by bending it with their immense gravity or by accreting material that emits bursts of radiation. In some cases, the presence of such objects might only be detectable through the subtle flickering of the stars they affect, making variable brightness a key clue in uncovering hidden cosmic secrets. As we continue to study these enigmatic systems, the mystery of variable brightness reminds us just how much we still have to learn about the universe. Each flicker and flare offers a glimpse into the complex interplay of forces that shape these stellar giants, challenging our understanding and inspiring new questions. Next, we'll venture into the search for life in these chaotic systems and explore whether such extreme environments could ever support habitable worlds. Now, shifting our gaze to one of the most profound questions in astronomy, let's explore the possibility of life in or around duodecuple star systems. Could such chaotic and extreme environments ever support habitable worlds? The answer is as complex as the systems themselves, but the search for life in these stellar neighborhoods opens up a fascinating discussion about the resilience of life and the adaptability of planets. In a duodecuple system, the sheer number of stars creates a dynamic and often hostile environment. Planets orbiting within such systems would face constant gravitational tugs from multiple stars, leading to unstable orbits and extreme temperature fluctuations. Imagine a world where the sun rises and sets multiple times a day, or where the climate shifts dramatically as different stars dominate the sky. These conditions would make it incredibly challenging for life as we know it to survive, let alone thrive. However, nature has a way of surprising us. Some scientists speculate that life could exist in the outer regions of these systems, where planets might orbit a single star at a safer distance, avoiding the chaos of the inner system. These planets could potentially maintain more stable conditions, with a single star providing consistent warmth and light. Even so, the gravitational influence of the other stars would still pose risks, such as occasional close encounters that could disrupt the planet's orbit or trigger catastrophic events like asteroid impact. Another intriguing possibility is the existence of life on moons orbiting gas giants within these systems. Just as Europa and Enceladus in our own solar system are considered potential havens for life due to their subsurface oceans, similar moons in duodecuple systems could harbor liquid water beneath icy shells. The gravitational interactions between the stars and the gas giants might even generate tidal heating, keeping these moons warm enough to support life. Yet the challenges don't end there. The intense radiation from multiple stars, combined with frequent stellar flares and magnetic storms, would create a harsh environment for any potential life forms. Protective atmospheres or magnetic fields would be essential for shielding life from these dangers, but building and maintaining such defenses would require a delicate balance of planetary conditions. Despite these obstacles, the search for life in duodecuple systems pushes us to think beyond the familiar. It challenges us to consider how life might adapt to extreme environments and what forms it might take. Could life evolve to withstand the constant changes in light and temperature? Could it find refuge in unexpected places like the shadowed craters of moons or the depths of subsurface oceans? These questions remind us that the universe is full of possibilities and the search for life is far from over. As we ponder these ideas, we're reminded of the resilience and creativity of life itself. Even in the most chaotic and unlikely places, the potential for life persists, urging us to keep exploring and questioning. Next, we'll delve into the role of cosmic dust in these systems and how it shapes the stunning yet elusive beauty of duodecuple star systems. Turning our attention to the ethereal beauty of duodecuple star systems, we encounter the enigmatic role of cosmic dust. This fine, scattered material, often overlooked, plays a dual role in shaping both the appearance and the mysteries of these stellar gatherings. On one hand, cosmic dust is the artist behind some of the most breathtaking nebulae in the universe. These vast clouds of dust and gas, illuminated by the light of multiple stars, create swirling patterns and vibrant colors that captivate astronomers and stargazers alike. The interplay of light and dust in these systems can produce phenomena like reflection nebulae, where starlight bounces off dust particles, or emission nebulae, where the dust glows as it absorbs and re-emits energy from nearby stars. Yet, for all its beauty, cosmic dust also presents a significant challenge to scientists. The same dust that creates these stunning visuals can obscure our view of the stars and planets within these systems. Imagine trying to peer through a dense fog that not only dims the light but also scatters it in unpredictable ways. This makes it incredibly difficult to observe the intricate details of duodecuple systems, such as the precise orbits of stars or the presence of exoplanets. Telescopes, even the most advanced ones, struggle to penetrate these dusty veils, leaving many questions unanswered. The dust doesn't just block light, it also absorbs certain wavelengths, making it harder to detect specific types of radiation that could reveal crucial information about the system's composition and dynamics. For example, infrared observations are often used to peer through dust, but even these methods have their limits. The sheer density of dust in some duodecuple systems can create a barrier that even infrared light struggles to penetrate. Despite these challenges, cosmic dust also holds valuable clues about the history and evolution of these systems. The dust particles themselves are remnants of ancient stellar processes, such as supernova or the collisions of smaller celestial bodies. By studying the composition and distribution of this dust, scientists can piece together the story of how these systems formed and how they have changed over billions of years. It's like sifting through the ashes of a cosmic fire to uncover the events that shaped the universe. As we continue to explore the role of cosmic dust, we're reminded of the delicate balance between beauty and obstruction in the cosmos. These dusty veils, while frustrating for astronomers, are also a testament to the complexity and richness of duodecuple star systems. Next, we'll delve into the dramatic impact of supernova in these systems and how these explosive events can reshape entire stellar neighborhoods. Now, let's shift our gaze to one of the most explosive events in the cosmos, supernova. In duodecuple star systems, these colossal stellar explosions don't just mark the end of a star's life, they can completely reshape the entire system. Imagine the sheer power of a supernova, releasing more energy in a single burst than our Sun will emit over its entire lifetime. In a system with 12 stars, the aftermath of such an event can be nothing short of chaotic. When a star in a duodecuple system goes supernova, the explosion sends shockwaves rippling through the surrounding space. These shockwaves can destabilize the orbits of nearby stars, potentially flinging them out of the system entirely or causing them to collide with one another. The gravitational balance that once held the system together can be thrown into disarray, creating a domino effect of instability. For stars that survive the initial blast, their paths may be altered in ways that defy prediction, leading to new and unpredictable interactions. But the impact of a supernova doesn't stop there. The explosion also floods the system with intense radiation and high-energy particles, which can strip away the atmospheres of nearby planets or even ignite new star formation in surrounding gas clouds. This dual role of destruction and creation is one of the most fascinating aspects of supernova. While they obliterate stars and disrupt systems, they also seed the cosmos with heavy elements like iron, gold, and uranium elements that are essential for the formation of planets and ultimately life. Evidence of past supernova in duodecuple systems has been found in the form of supernova remnants expanding shells of gas and dust that mark the site of these ancient explosions. These remnants often glow brightly in X-rays and radio waves, providing astronomers with a window into the violent history of these systems. In some cases, the remnants are so vast that they envelop multiple stars, hinting at the sheer scale of the original explosion. By studying these remnants, scientists can piece together the timeline of supernova events and their lasting effects on the system. One particularly intriguing discovery is the presence of neutron stars or black holes in duodecuple systems, which are often the remnants of supernova. These dense, compact objects can exert a powerful gravitational influence on their surroundings, further complicating the dynamics of the system. In some cases, they may even trigger new rounds of stellar collisions or mergers, perpetuating the cycle of chaos and renewal. As we reflect on the impact of supernova, it's clear that these events are both destructive and transformative. They remind us that even in the vastness of space, change is constant, and the universe is always in a state of flux. Next, we'll uncover the mystery of stellar twins in duodecuple systems and how their existence challenges our understanding of star formation. Now, let's turn our attention to a discovery that has left astronomers both fascinated and puzzled: the existence of stellar twins in duodecuple star systems. These identical twin stars, born from the same cosmic cradle, share nearly identical masses, temperatures, and compositions. At first glance, they might seem like a cosmic coincidence, but their presence in such complex systems raises profound questions about how stars form and evolve. In most star systems, stars vary widely in size, brightness, and composition. But in duodecuple systems, astronomers have observed pairs of stars that are so similar they could be mistaken for one another. These stellar twins challenge the traditional models of star formation, which suggest that stars form from collapsing clouds of gas and dust with enough variation to produce a diverse range of stellar types. So, how do these twins end up so perfectly matched? One leading theory is that these twins formed from the same dense pocket of material within a massive molecular cloud. As the cloud fragmented, it created two nearly identical clumps of gas, which then collapsed under their own gravity to form stars with strikingly similar properties. Another possibility is that these twins were once part of a larger group of stars that interacted gravitationally, with the most similar stars pairing up while others were ejected from the system. This process, known as dynamical sorting, could explain why some duodecuple systems host such perfectly matched pairs, but the mystery doesn't end there. Stellar twins also challenge our understanding of stellar evolution. In most cases, stars evolve at different rates depending on their mass and composition. Yet, in these systems, the twins appear to age in lockstep, maintaining their similarity over billions of years. This raises questions about whether external factors, such as the gravitational influence of other stars in the system, play a role in keeping these twins synchronized. The discovery of stellar twins also has implications for the search for exoplanets. If planets form around these stars, they would likely experience very similar conditions, potentially leading to the formation of nearly identical worlds. This opens up intriguing possibilities for studying how planetary systems develop in such unique environments. As we unravel the mystery of stellar twins, we're reminded that the universe is full of surprises. These identical stars not only challenge our understanding of star formation, but also hint at the intricate processes that shape the cosmos. Next, we'll explore the role of exotic matter in duodecuple systems and how it might explain some of their most puzzling properties. Now, let's venture into a realm that pushes the boundaries of our understanding: the role of exotic matter in duodecuple star systems. While we're familiar with the ordinary matter that makes up stars, planets, and even ourselves, exotic matter is something entirely different. It's a theoretical concept that challenges the very fabric of physics, and its potential presence in these complex systems could explain some of their most baffling behaviors. Exotic matter refers to forms of matter that don't conform to the standard rules of physics as we know them. Unlike ordinary matter, which is made up of protons, neutrons, and electrons, exotic matter could include particles with strange properties, such as negative mass or the ability to warp spacetime. While these ideas might sound like science fiction, they're grounded in serious scientific theories, and duodecuple star systems might just be the perfect place to look for evidence of their existence. One of the most intriguing possibilities is that exotic matter could play a role in stabilizing these chaotic systems. With 12 stars orbiting one another, the gravitational forces at play are incredibly complex, and traditional models struggle to explain how such systems remain intact over billions of years. Some scientists speculate that exotic matter, with its unique properties, could act as a kind of cosmic glue, helping to balance the gravitational tug-of-war between the stars. This could explain why some duodecuple systems appear to defy the odds, maintaining their structure despite the intense forces at work. Another theory suggests that exotic matter might be responsible for some of the strange energy signatures observed in these systems. For example, certain duodecuple systems emit bursts of energy that don't align with the behavior of ordinary stars. These anomalies could be the result of interactions involving exotic particles, which might release energy in ways we don't yet fully understand. If proven, this would not only shed light on the mysteries of duodecuple systems, but also open up new avenues for exploring the fundamental nature of matter itself. The search for exotic matter in these systems is still in its early stages, but the implications are profound. If exotic matter exists, it could revolutionize our understanding of the universe, from the smallest particles to the largest cosmic structures. It might even provide clues about the nature of dark matter and dark energy, two of the biggest unsolved mysteries in modern astrophysics. As we continue to explore the strange and wonderful world of duodecuple star systems, the possibility of exotic matter reminds us that the universe is far more complex and mysterious than we can imagine. Next, we'll take a look at the future of duodecuple system research and the cutting-edge technologies that could help us unlock their secrets. As we turn our gaze toward the future, the study of duodecuple star systems is entering an exciting new era. Scientists are now equipped with advanced tools and technologies that promise to peel back the layers of mystery surrounding these cosmic wonders. One of the most promising developments is the next generation of space telescopes designed to observe the universe with unprecedented clarity. These instruments, like the James Webb Space Telescope and its successors, are capable of capturing detailed images and spectra of distant star systems, allowing researchers to analyze their composition, dynamics, and even the faintest traces of exotic matter. Ground-based observatories are also playing a crucial role in this quest. Facilities like the extremely large telescope, currently under construction, will have the power to resolve individual stars within these complex systems, even those located thousands of light-years away. By combining data from space and ground-based telescopes, astronomers hope to create a more complete picture of how duodecuple systems form, evolve, and interact over time. But it's not just about better optics. Advances in computational modeling are revolutionizing our ability to simulate these chaotic environments. Supercomputers can now run highly detailed simulations that account for the gravitational interactions of 12 stars, their magnetic fields, and even the effects of hypothetical exotic matter. These models help scientists test theories and predict behaviors that can then be verified through observation, creating a powerful feedback loop between theory and experiment. Another exciting frontier is the development of new detection methods. For example, gravitational wave observatories like LIGO and Virgo are beginning to explore the possibility of detecting ripples in spacetime caused by stellar collisions or mergers within duodecuple systems. Such events could provide direct evidence of exotic matter or other phenomena that challenge our current understanding of physics. The future of duodecuple system research is not just about answering existing questions, it's about uncovering entirely new ones. As we push the boundaries of technology and knowledge, we may discover phenomena that redefine our understanding of the universe. From the role of dark matter to the potential for life in these chaotic environments, the possibilities are as vast as the cosmos itself. With every new discovery, we're reminded that the universe is full of surprises, and duodecuple star systems are among its most enigmatic treasures. As we continue to explore, one thing is certain: the journey to unravel their secrets is just beginning. As we bring our journey through the mysteries of duodecuple star systems to a close, it's clear that these cosmic marvels are more than just a collection of stars. They're a window into the universe's most perplexing secrets. From the chaotic gravitational dances of 12 stars to the strange radio signals that hint at unknown phenomena, each discovery has pushed the boundaries of what we thought possible. These systems challenge our understanding of star formation, stellar lifespans, and even the fundamental forces that govern the cosmos. They remind us that the universe is far stranger and more complex than we could ever imagine. But the story doesn't end here. Every new observation, every groundbreaking simulation, and every technological advancement brings us closer to unraveling these cosmic puzzles. The future of duodecuple system research is bright, filled with the promise of even more astonishing discoveries that could reshape our understanding of the universe. If you've enjoyed this deep dive into the mysteries of duodecuple star systems, don't forget to share your thoughts in the comments below. What discovery fascinated you the most? And if you're as captivated by the wonders of space as we are, make sure to hit that subscribe button and ring the notification bell. There's so much more to explore, and we can't wait to take you on the next cosmic adventure. Until then, keep looking up. The universe is full of surprises waiting to be uncovered.